Hello everyone, today we will explore a text classification model using LSTM bidirectional LSTM. We will walk you through the entire process from data pre-processing to model training and testing and discuss the performance metrics of these models. The primary focus of my assignment is on the task of spam detection of SMS. As we all know, spam messages are a nuisance in our digital lives and effectively detecting them is crucial. I will showcase two different deep learning models for this purpose, LSTM and bidirectional LSTM. I'll understand why I'll start why I choose these models and then proceed with the detailed comparison. The reason why I have chosen LSTM and bidirectional LSTM for my text classification task is because LSTM excels at processing sequence of data, making it ideal for text analysis. Its ability to capture long-term dependencies in data sets it apart. Additionally, I have also exploring bidirectional LSTM, which not only looks at the past but also the future context of a word in sequence, providing potentially richer information. So when coming to the code, here I have I imported the date. I mean, here I have imported the necessary libraries and I have used Python libraries like NumPy, Pandas for data handling, TensorFlow for deep learning, and other tools for visualization and evaluation. The first step is for any machine learning project is to load and understand the data. In our case, we are reading the SMS spam data from a file and organizing it into a data frame. To make it the text data consistent and suitable for machine learning, I have converted all the message column to a lowercase using the string.lower function, and this ensures a uniformity in the text and prevents potential discrepancies when analyzing it. Since text data cannot be directly fed into the neural network or RNN or LSTM, I have performed tokenization to convert words into numerical values. I have used the tokenizer class from TensorFlow .keras.preprocessing.text to accomplish this. The fit underscore on text method use it to fit the tokenizer to the text data and create a vocabulary. The number of unique words in the vocabulary is stored in vocab size. Next, I have used the text to sequence method to transform text messages into sequence of numbers based on the vocabulary. These sequences may have different lengths, so I have used pad sequences to ensure all sequences have the same length by padding them with the 0. The maximum sequence length is calculated and used to pad all sequences consistently. In this step, I have included all the labels ham and spam as numerical values. Ham is mapped to 1, 0, and 0, and spam is mapped to 1. In this transformation is necessary for binary classification, where I wanted the model to distinguish between spam or ham. In the context of spam detection, it's common for the data set to be imbalanced with fewer spam values or fewer values. And so in order to address this imbalance, I have applied smart a technique for oversampling the minority class to balance it with the majority class non-spam. This ensures that the model does not become biased towards the majority class. After applying the smart, it's important to verify the distribution of the classes in the data set. The code calculates the count of the count classes of 0 for non-spam and 1 for spam to ensure that oversampling process effectively balances the data set. Before training a model, a machine learning model is crucial to split the data set with training and test set. The training set is used to train the model and testing set is used to evaluate its performance. I have used the train underscore test underscore split function from a scalar in order to divide the data into training and testing set with 80% for training and 20% for the testing. So the code chunk here we see here pertains to the creation of an LSTM deep learning model. Let's break it down step by step. I have created an instance of sequential model using model underscore LSTM. The sequential model allows us to build a neural network layer by layer. The embedding layer is added, which is responsible for converting the words into dense vectors of fixed size. It helps the model understand the relationship between words. Spatial dropout 1D is added as a dropout layer, since dropout is a regularization technique that prevents from overfitting, and spatial dropout 1D applies dropout to the entire 1D feature, one-dimensional feature map. The heart of the model is the LSTM layer. LSTM is the type of recurrent neural network that excels for sequence data. I have specified the number of LSTM units in the form of LSTM 64 to determine the model complexity. Another dropout layer is added to the LSTM layer in order to avoid the overfitting. Finally, a dense layer with the single unit and the sigmoid function, activation function is added. This layer is responsible for making the final prediction, classifying messages as spam and non-spam. The model loss function is defined as a binary cross entropy, and the Adam optimizer is used. We are interested in monitoring the accuracy during training. Early stopping is a regulation technique that helps us prevent the overfitting. Here we have used early stopping also with the patient is number of is equal to 5. And the code snippet trains the LSTM model. LSTM model and with the epoch, with the 50 number of epochs with the batches of 32, a validation split of 20%. So after training the LSTM model, I have evaluated its performance, and the loss keep on decreasing and the accuracy keep on increasing and decreasing. Both are happening, and we have achieved a accuracy of 48%. And like early stopping made our model to stop because it have observed overfitting of the data. So when coming to the bidirectional LSTM, previously the LSTM is having a very less accuracy. So we have implemented bidirectional LSTM, and after training this model, we are able to see the loss keep on decreasing and the accuracy keep on increasing. So we have achieved a accuracy of 92.95%. So we are defining the learning curves here, and we can see that there is a overfitting of the data is happening for the LSTM. And when coming to the graph of the bidirectional LSTM, we can see that there are model curves. I mean, there are train loss, train accuracy. There is no overfitting is happening. And when coming to the confusion matrix, we can see that there are there are no true positives and true negatives in the confusion matrix of LSTM. And in bidirectional LSTM, there are all are I mean, true positives. Every aspect of the confusion matrix is satisfying. And when here we are testing all the sample messages which I have collected from the humans, and we have tested with our existing model, and we can see that LSTM is actually giving all the messages as spam. Even ham messages are present. And when comes to the bidirectional LSTM, it is creating spam as spam and ham as ham. Like suppose let us take an example of message: congratulations, you have won a free iPhone. In this case, it is actually a spam message. So our bidirectional LSTM training model is actually predicting it as a spam. And when coming to the loose, I mean, don't forget to pick up groceries on your way home message. It is predicting it as a ham. So it is a ham message, and it is predicting it as a ham. So our model is working perfectly according to this analysis. So I mean, there are like the loss function optimizer and monitoring metric same as the LSTM model for the bidirectional also. And I mean, due to the higher which is achieved in the bidirectional LSTM when compared to the LSTM, we select the bidirectional LSTM as well. Thank you for joining me in this presentation. I hope this deep dive into the text classification using LSTM and bidirectional LSTM helps is informative.